In section 2, we're going to take a look at conditional probability and independence. In section 1, we saw that one way we can display information to find probability was through a two-way table. But another way we can represent events is with a Venn diagram, which is a display of potential probabilities. So the box around the Venn diagram represents the total sample space, where that probability is 1. The circles themselves represent the probability of each event. So for example, if I have two events, A and B, I have my sample space S, and then I have my event A and my event B. So when we're reading it, the probability of A is all of circle A. That includes any overlap it shares with circle B. And then the probability of B is all of circle B, also any overlap it may share with A. And then the probability of A and B is the overlap. So we're actually going to introduce the probability of A and B as well. So in section 1, we talked about the probability of A or B. We briefly talked about the probability of A and B as well when we're looking at the table. So we're also going to talk about it as well in section 2. One of the things we haven't discussed is the notation we use for probability. So far I've been spelling out the word or and the word and when we've been finding probability, but there are actually notations for it. So one of them is called a union. So that represents or. It says the probability that either or occurs. So we use the U, which represents union. So you would write it as the probability of A or B. The other one is and, so that's the probability that both occur. And this is called our intersection, which is written as the probability of A and B. So let's do a few examples where we can see how this works with our Venn diagram. So let's look at an example if I were looking at the probability of A. So we have our sample space. We have our two events, A and B. Then the probability of A is all of circle A. So as I discussed previously, it does include the overlap it shares with B. The probability of B, so again, sample space with our two events A and B. It would be all of circle B, including the overlap it shares with A. Next, we have the probability of A and B. Which is just the overlap, which would be just everything in the middle. And then let's look at the probability of A or B. So we have our sample space. So that would be everything in both circles. So not everything outside of the circle, because that represents not A and not B, but the two circles together would be A or B. All right, so let's look at some not probabilities. So we looked at the probability of A, the probability of B, and an or, but let's see how that affects if you're trying to find the probability of A and not B, or vice versa, and then both. So we have our sample space. We have A and B. So I want the probability of A and not B. So the only difference between this and the probability of A, which is what we looked at above, is I'm still highlighting circle A, but I'm not including its overlap with B. So this is basically saying that I only want A, I don't want anything that it also shares with B. So then for our next example, this says not A or B. So the first thing I do is I highlight everything that is not A, which would be just circle B, very similar to what we did. But I'm also saying, this is B, and then I want everything that is not A. So this would include everything outside the sample space as well. So this is everything that is not A or B. So I basically have everything that is not in circle A, including any overlap it shares with B. Okay. Then in our last example, we have the probability of not A and not B. So the space that is everything except A and B, basically, is everything outside the two circles. So it's everything that's not in A and not in B. So not in either circle and not in their overlap. So these are just a few examples of how probability works when looking at Venn diagrams visually. Now we're going to go ahead and do an example. So a study was done as to whether parents who were spanked as children are more or less likely to spank their own children. 200 parents were interviewed anonymously, and it was found that 125 were spanked as children, 92 spank their children now, and 74 are in both categories. We want to make a Venn diagram, and then we're going to answer our probability questions. So I'm going to divide my two events. So I'm going to let event A be that a parent was spanked. And then I'm going to let event B be that a parent spanks now. It is important that you define your events before you do a Venn diagram. Since you get to pick which one is event A and event B, which then impacts what your Venn diagram looks like, you have to define your events ahead of time. So I'm going to draw my sample space. Then I'm going to have my two circles. So I have A and B. When you are completing a Venn diagram, you have to start with the overlap. You have to start with and. So in this case, I'm starting with my 74. So those are the parents that do both. They were spanked as a child and spank their children now. The reason I start with this is that the 125 that were spanked as children, when I go to do event A, also includes any overlap with B. So the probability of event A, I have to do 125 minus 74. And that gives me the parents that were only spanked as children. So 51. And then if I add those together, I get all of the parents who were spanked as children. Then I have to do the same thing for event B. I have to take my 92 who spank their children now and subtract the 74 who were also spanked as children. And I get 18. My last is to find my neither. So far I have accounted for the parents who were spanked and the parents who spank their children now. But if I add 51, 74, and 18, I don't get 200, which is what my total sample space involves. So I have to do, when I add those together, I get 143. Then I'll do 200 minus 143, and I get 57 who fall outside, who were not in either category. So now that my Venn diagram is done, I can go ahead and find some probabilities. So my first one is that I want to find the probability that a parent was spanked and spanks now. So that's the probability of A and B. So that's my overlap, 74 over 200. Which, when I simplify, is 37 over 100. The next one I have, a parent was spanked or spanks now. So that's the probability of A or B. So this is a little bit easier to do with a Venn diagram because as we saw when we highlighted, I want everything in A and B. So I do 51 over 200 plus 74 over 200 plus 18 over 200. So that accounts for everyone who was spanked or spanks now, which gives me 143 over 200. Another way to think of this is if a parent was spanked or spanks now, I'm basically saying everyone except the neither. So my other option here was to do 1 minus the 57 over 200. Third one says a probability that a parent was spanked but doesn't spank now. So that's the probability of A and not B. So that is just, as we know from our previous page, just circle A without any overlap with B. So 51 over 200. And then for D, we have a probability a parent wasn't spanked but doesn't spank now, but does spank now. So that's the probability of not A and B. So we didn't do this on the previous page, but it works very, very similar to C. So I just want the people that are in circle B without any overlap from A, which is 18 over 200, which does simplify to 9 over 100. In E, we want the probability a parent was neither spanked nor does spank. So that's the probability of not A and not B, which is everything outside our two circles, which we found to be 57 over 200. The last thing that we're going to do on this problem is determine mutually exclusive in terms of a Venn diagram. So the F says the probability a parent was spanked or spanks now, but not both. So this is basically asking if our events are mutually exclusive. So the way that looks, so that's basically saying the probability of A or B. But not the overlap. So we have to do 51 over 200 plus 18 over 200, which gives us 69 over 200. So even though it says A or B, it's not the same thing as what we did in B, which was literally saying I can do a parent was spanked or spanks now. I can also include both. But F is saying specifically if these two events were mutually exclusive, I want just A and just B added together. I don't want to include any of the parents that are in both categories. All right, next we have that a pizza shop has two sizes of pizzas, large and small. On a certain day, a pizza shop made 59 plain pizzas and 72 pizzas with toppings. Of the 59 plain pizzas, 19 were small, and of the 72 pizzas with toppings, 42 were large. A pizza is chosen at random. Find the following probabilities. It does say make a two-way table and a Venn diagram to display the information, but I'm just going to do a two-way table just because there's 4 things going on here, and it makes it a lot more difficult to do a Venn diagram when you have multiple things happening at once. Unlike our previous example where we're just saying, all right, either was spanked or not spanked, but this time I have to take into account small pizza, large pizza, plain with topping. So it's just easier to do the two-way table. So I'm going to make my left side whether or not it was my rows plain or with toppings. And then I have my total. And then my columns are going to be small, large, and total. So we know that they made 59 plain pizzas. So that is my total number of plain pizzas. And they made 72 pizzas with toppings. So those are totals, which then gives me the total number of pizzas made, 131. We know of the 59 plain pizzas, 19 were small. And of the 72 pizzas with toppings, 42 were large. With this information, I can finish completing my table. So I do 59 minus 19, and that gives me how many of the plain pizzas were large, which is 40. And if I do 72 minus 42, that gives me how many of the pizzas with toppings were smalls, which is 30. And then I can add to get my totals for my columns, which are 49 and 82, which does also add to 131. So all of my math was done correctly. So let's go ahead and do some probabilities. So probability of pizza is a large, so probability of large. So 82 over 131, which is approximately 0.63. Next one is the probability you get a small pizza, which is 49 over 131, which is approximately 0.37. Next, we want to find the probability you get a pizza with toppings. So that's 72 over 131, which is approximately 0.55. Next, we have the probability of a plain pizza, which is 59 over 131, which is approximately 0.45. Okay, so far we've done just single probabilities, which has just been the totals from a row or a column. Now we're going to do some combinations. So for E, I want the probability I get a large plain pizza. So that's the probability of large and plain. So I'm looking for the overlap in the table. So I go to large plain pizzas, and I get 40 over 131, which is about 0.31. Next, we have a small with toppings. So that's the probability of small and toppings, which if I go to my table, there are 30 out of the 131, which is about 0.23. So those are examples of and. So they don't specifically say the word and, but we know that they're and. Or will specifically say or. That's the only way to really interpret an or probability is if it says the word or. So small or plain. So when I'm doing that, I have to do the probability of small plus the probability of plain minus the overlap. So my small and plain. Because in our table, we've seen that I can have a small plain pizza. So they are not mutually exclusive events. So the probability you get a small is 49 over 131 plus the plain, 59 over 131, minus both 19 over 131, which gives 89 over 131, which is approximately 0.68. And our next one, we want large or with toppings. So I have to do the probability of large plus the probability of toppings minus the probability you get a large and it has toppings. So large we know is 82 over 131 plus my toppings, 72 over 131, minus my larges that have toppings, 42 over 131. And we get 112 over 131, which is approximately 0.85. So So the last one is small or large. So this is an example of mutually exclusive because I cannot get a pizza that is both a small and a large. So I don't have to worry about any overlap. So I can do the probability of small plus the probability of large. So I get 49 over 131 plus 82 over 131, which gives me 131 over 131, which is 1. Which makes sense here. Since those are my only two options, it makes sense that when I add their probabilities together, I'm going to get 1. Because I either have a small pizza or I have a large. There's no third size. So when I add them together, I get everything. So far, when we have talked about and probability, we have been specifically looking at a Venn diagram or a table. But there is another way to calculate and probabilities, and that's using the multiplication rule. So for example, we have that you roll a die 2 separate times. And we want to find the probability that you get an even number followed by a 5. So there's 2 ways to do this. Is you can actually go through the sample space and count the outcomes like we did previously. So we already know the sample space for rolling 2 dice is 36. So even number 2 followed by the number 5. So 2, 5, I can get 4, 5, or I can get 6, 5. So that tells me there are 3 out of the 36 outcomes, which is 1/12. So that's one way to go about it. The other way is using our multiplication rule. So that's doing it separately. So the probability you get an even number on a die, 3 out of 6, which is 1/2. The probability you get a 5 is 1/6, because there's only 1 5 on a die. So the probability you get an even number and a 5 is you multiply those probabilities together. 1/2 times 1/6, which gives us 1/12. Which is a lot easier, especially if you can't remember all of the possible outcomes and if you make a mistake in figuring out all of the outcomes from the sample space. So if we want to find the probability that 2 more events occur together, then we multiply the probabilities. So the probability of A and B has its own formula, which is the probability of A times the probability of B. Very important distinction here is this only works if the events don't influence one another. So that ties with independence, which we'll talk about here in a little bit. So you can only multiply the probabilities together if the events are independent. So the probability of rolling an even number does not influence the probability I roll a 5. So I can just go ahead and multiply those together. So let's do a few examples. So you roll 2 dice, one of them is red and one of them is green. We want to know the probability that you roll a red 1 and a green 5. So that's the probability of a red 1 and a green 5. So I can do these separately. So getting a red 1, 1/6, times a green 5, 1/6, which gives me 1/36. Second example, a coin is flipped and a die is rolled. What is the probability that the result is heads and a 6? So the probability you get heads and a 6. So the probability of flipping heads, 1/2, times the probability you roll a 6, 1/6, which gives us 1/12. Last example we have, what is the probability that a couple will have 4 boys in a row? So that's probability you get boy and boy and boy and boy. As we've already discussed in our previous section, these events are not influenced by one another. So it's going to be 1/2 times 1/2 times 1/2 times 1/2. Because previous outcomes in this case do not influence my next outcomes, which is going to give 1/16. So the examples we just did have to do with independent events. So what happens if two events are dependent, which is what we're going to discuss next. So dependent events, also known as conditional probability, that's when we assume events do not influence each other, so independent events. A couple things for us that are always going to be independent are coins and dice. Okay. Or combining those two. Never going to influence. These are always going to be independent events. However, there are cases where they do influence events. So conditional probability is the probability that one event will happen if it is known that another event has happened. So the symbol for conditional probability is you read it as the probability of A given B. So we use a vertical line. So that vertical line means the word given. So it's saying what's the probability that, so what that means is the probability A occurs given B has already occurred. Okay. So for that formula, the probability of A given B is the probability of A and B over the probability of B. If you're trying to find the other way, so you want to find the probability of B given A, the numerator is still the same. It's the probability of A and B, but the denominator is now the probability of A. So whichever event you're saying has already occurred will always be your denominator, and the probability of both occurring will always be your numerator. So another way to think of this is in a picture. I think it's kind of easier to kind of visualize what that means in a picture. So when we know something has happened, it changes the sample space. It specifically shrinks it to the given event. So if I want to look at this visually, I have event A and I have event B and I have my sample space. So if I want to find the probability of A given B, I'm saying event B has already occurred. So I am restricting my sample space to only where B is. So that's my denominator, the probability of B. My numerator, I'm now saying is, what's the probability that now A happens, which is the only place where A happens when B has already occurred is their overlap, which is where we get the formula from. So the only way A can happen if B has already occurred is if you look at the intersection. So for the formula, so then given that conditional probability, we can then manipulate that formula to find the probability for dependent events. So just kind of review. So we have the probability of A given B is the probability of A and B over the probability of B. So multiplication is A and B, which means if I want to find the probability of A and B, knowing my events are dependent, I solve this formula by multiplying both sides by the probability of B. So that gives me that the probability of A and B is the probability of B times the probability of A given B. So this formula is specific to dependent events. So if you know two events are dependent, this is the formula you use to find the probability of A and B. So you can't just strictly multiply your two outcomes together. So let's do an example using that hair color and eye color that we had at the end of our last note. So we have the black, brown, red, and blonde, and the eye colors of brown, blue, hazel, and green. And this time we already have our totals. So if we select a woman and find she has brown hair, what is the probability that she will also have hazel eyes? So a couple things to kind of notice here is it says the word if. That indicates conditional probability. Given is also used, but if is also another common word. So it's not only that you're going to see the word given, you might also see the word if. So that tells me that brown hair is my event B. This is my event that has already occurred. What is the probability that she will have hazel eyes? That's my event A. I'm trying to find, right, now that I know that I'm looking at only women with brown hair, I want to know how many of them have hazel eyes. So probability of A given B. So I've restricted it to my brown hair. So my brown hair. So I'm only looking at that row. Now I want to know how many of them also have hazel eyes. So if I look, 29 of them. So that is going to be my A and B is 29 over just my total of brown hair, 143. And then 29 over 143 is approximately 0.20. Now let's say if we select a woman and find she has brown eyes, so here we have the if, what is the probability she also has black hair? So brown eyes is my event B, it's already taken place, and then black hair is my event A. So restrict it to my brown eyes, so this time I'm restricting it to a row, so brown eyes, and of those, how many of them have black hair? 36. So my probability of A given B is going to be 36 over 122, which does simplify to 18 over 61, which if you want to think in terms of a decimal is approximately 0.30. So that's how we do conditional probability from a table, which is a lot easier than it seems because you are restricting to a row or a column, and that's the total you use. All right, so showing independence. So we've talked about finding probability for independent events, finding probability for dependent events, but how do we know whether or not two events are independent or dependent? We've already kind of talked about the fact that coins and dice are always going to be independent, but for anything else, how do we know whether or not two events are independent? So it goes back to our formula. So if two events are independent, we know that the probability of A and B is just the probability of A times the probability of B. If two events are dependent, we know the probability of A and B is the probability of B times the probability of A given B. Since these are both formulas for the probability of A and B, I can set them equal to each other. I can say if two events are independent, the probability of A times B should equal the probability of B times the probability of A given B. And if I notice here, both sides have that probability of B. So I can go ahead and cancel that out because the probability of B would be the same in both cases. So that gives me that if two events are independent, you want to show that the probability of A equals the probability of A given B. Because if they're equal, then they're independent. So let's go ahead and do an example. So we have that the U.S. Center for National Health Statistics compiled information about injuries in the United States. The frequencies below are in millions. So we have broken down by gender, male and female, and their injuries, whether or not they occurred at work, home, or other. And then we have our totals. We want to know, are the events female and home circumstance independent? So A is going to be female, B is going to be home circumstance. So I want to find the probability of A, so the probability you're female, which is 25.8 over 61.4. And I want to find the probability of A given B. So the probability of A and B, so female and home, which is 11.6, over the total number of injuries that occur at home, 21.4. Now, these fractions don't look the same, so I want to go ahead and find their decimal. So 25.8 divided by 61.4 is approximately 0.42. 11.6 divided by 21.4 is approximately 0.54. So I can see the probability of A does not equal the probability of A given B, which means these events are dependent. In our last example, we're going to talk about how we can use our mutually exclusive or general addition rule for probability and independent/dependence to find probabilities. So we know the probability of A is 0.44, the probability of B is 0.22. We know A and B are independent, so we want to find the probability of A or B. So the first thing to notice here is that because the events are independent, that tells me that the probability of A and B is the probability of A times the probability of B. I do not know these events are mutually exclusive. So when it comes to my probability of A or B formula, I have to use the probability of A plus the probability of B minus the probability of A and B, because I don't know they're mutually exclusive. The only thing I know is that they're independent. So the probability of A is 0.44 plus the probability of B, which is 0.22. So because they're independent, my A and B is 0.44 times 0.22. Which is going to be 0.0968. So I'm going to subtract that. So 0.44 plus 0.22 minus 0.0968. And that gives me 0.5632 as my probability for A or B. Let me know if you have any questions about Venn diagrams, two-way tables, finding probability, conditional probabilities, probabilities from Venn diagrams, just anything from section 2. Let me know if you have any questions over it.